Good afternoon, dear students. So, previously we have discussed about inertial frames of references and how to apply the Newton's first law and second law to the inertial frames of references. Today, let us discuss a particular case in which, right, in which there is an inertial frame of reference, and let us suppose it is S, and there is one more frame of reference which is, let it be S dash, non-inertial, right? So this is inertial frame of reference. This is inertial frame. Okay, and the next thing is this frame of reference is non-inertial frame, right? See, non-inertial means if there is a frame which is inertial frame of reference, it means its acceleration is zero. Non-inertial frame of reference means this frame is moving with some acceleration, let it be a naught. Let us consider a particle P, right, which is present in non-inertial frame of reference. Now we have to calculate the acceleration of the particle which is present in non-inertial frame of reference. Right? So to calculate that, in the previous example, previously we have discussed that if there is an inertial frame of reference S and another frame of reference S dash is moving with uniform velocity, u, this is uniform velocity, then this already told, S is already told that it is inertial frame of reference. It means the acceleration is zero. Okay, and its acceleration also zero, right? Whatever the frame of reference S dash is moving with uniform velocity, right, then its acceleration also zero. The acceleration of, right, frame of reference, that is S dash, is also zero. Then the acceleration of the particle also will be zero. Then the acceleration of the particle, that is AP, right? If you consider a particle P here, right, so AP also zero, if and only if the net force acting on the particle is zero. So this, all these, A equal to 0, A dash is equal to 0. From this relation we got AP with respect to acceleration of the particle with respect to the frame of reference S is 0. So I will denote the acceleration of the particle AP, acceleration of the particle with respect to the frame of reference S, let it be APS, and that will be written as the acceleration of the particle with respect to the frame of reference S dash, and acceleration plus acceleration of the frame of reference S dash with respect to S. So from this we can write that. So by using this relation, so here is a frame of reference S dash, and in this frame of reference particle P is present. So we need acceleration. I want to write the equation for the acceleration of the particle with respect to the frame of reference, acceleration of the particle with respect to the frame of reference S dash. Okay, that is equal to, I'll write here, so the equation will be acceleration of the particle with respect to the frame of reference S dash equal to acceleration of the particle with respect to S minus acceleration of the frame of reference S dash with respect to S. So we can write that, let let, because already the frame of reference is moving with an acceleration a naught. The frame of reference s dash is moving with an acceleration a naught, and then the particle also along with frame of reference s dash, particle p is also moving, so it will have an acceleration, let it be a. So in the place of, we can write that here in the place of a p s dash, in the place of a p s dash, okay, we can write a. So this will be the equation, right? So a p s dash equal to a p s minus a s s dash s dash s. Now this is a equal to aps, so let it be acceleration aps, okay, minus a s dash s is nothing but a naught, multiply with m, multiply this equation with m on both sides. So m into a equal to m into aps minus m into a naught. See, according to Newton's second law, see here, this is the acceleration of the particle with respect to the frame of reference. As the particle is moving along with frame of reference, right? So there will be a force acting on this particle, on the particle P. So we can write it as, let's see, the product of mass and acceleration of the particle will be equal to the force, net force will be equal to the net force. So I can write it as ma equal to f minus ma naught, ma naught, and I can solve from this equation. See, from this equation, that is ma equal to f minus m a naught. I can solve for acceleration a equal to, we need the acceleration of the particle with respect to the frame of reference s dash, that's what we have written. See here, a p s dash, acceleration of particle with respect to s dash, we have labeled it as a, that we are going to calculate. So a equals to f minus m a naught, m a naught divided by m, right? So generally if, right, generally if a particle is moving with a net force, if a particle is moving with an acceleration a and a net force f is acting on it, okay, if both the frames of references are inertial, then we can write acceleration of the particle of mass m as f divided by m. But in the above equation also we have written f by m quantity is there, but minus ma not also there, right? Why? Because why we are writing this? Because along with the frame of reference s dash, the particle is moving. The frame of reference, the frame of reference s dash, the frame of reference s dash is also non-inertial. If this frame of reference is inertial, then we can write the equation a equal to f by m. We can write the equation a equal to f by m. Since the frame of reference s dash is also non-inertial, means the frame of reference s dash is also having certain acceleration a naught, that's why m into a naught quantity should be subtracted from the force, from the net force. This is the net force acting on the particle. From this net force we have to subtract m minus a naught, then this total quantity is the net force acting on a particle which is present in non-inertial frame of reference. So this is a particle present in non-inertial frame of reference S dash. Then the net force acting on this particle will be F minus A naught. Because of acceleration of the frame of reference S dash, this quantity is coming into consideration, and this quantity, that is minus ma naught quantity, right, minus ma naught quantity is called as pseudo force. Okay, so today's our topic is, we have discussed about pseudo forces. This is our topic. Pseudo forces. Okay, so when there is a non-inertial frame of reference means if a frame of reference is moving and it's not moving with uniform velocity, it is having some acceleration a naught, it has some constant acceleration a naught. Okay, in that case pseudo forces will come into action. Here the pseudo force is ma naught quantity minus ma naught quantity is called a pseudo force, right? And after that, now let us discuss about a very important case in the daily life, which is horse and cart. So what is this horse and cart concept? Horse and cart. See here, all of you might have observed, right? The cart. Okay, horse. Okay, horse cart. See, this is this is horse, right? Okay, so when the horse is pulling, let us suppose a horse is applying a force F1 in the forward direction. According to Newton's third law, there will be a backward force which is applied on horse, equal and opposite force F2, let us suppose. Okay, when the horse applies a forward force F1 on the cart, according to Newton's third law, cart also applies, okay, equal and opposite force F2 on the horse. It means both F1 and F2 are acting in the opposite directions. They are equal, F1 equal to F2, but their directions are opposite. Both F1 equal to F2, but they both are acting in opposite directions. Then two equal and opposite forces are acting. What will be the resultant force? Actually, the resultant force means net force will be F net will be equal to 0. F net will be equal to 0. See, there is F net is 0 when net force is 0. When net force is 0, will the body be accelerated? For example, here the horse is applying a forward force F1 and cart is applying a backward force F2. Combination of both is becoming 0. Then how the horse and cart is able to move forward? Generally you can observe that when the horse rider or a driver of the cart whips the horse, it pulls forward, then the cart will move forward. See, the motion of the body is possible when there is only certain amount of net forces acting. But in this case, in the case of cart and horse, the net force is becoming zero. Still, even though the net force is zero, the cart and horse are able to move forward. They are moving forward. How? Why are we getting this contradictory situation? Where did we commit the mistake? We have committed a mistake that we haven't decided which one is the system. Which one is the system? We are just told that horse is applying a force F1 on cart in the forward direction, and cart is applying a force F2 on horse in the backward direction. But we haven't told which one is the system to be considered. Here, out of cart and horse, we can consider cart as a system, or horse as a system, or horse and cart together as a system. But when we are discussing this F1 net force, we haven't decided the system. Okay, right. Now, let us decide that our system is cart. Let us decide that our system is cart. Okay, now let us try to write the forces acting on cart. Let us try to write the forces acting on cart. Right? And now, you see here, so what are the forces acting on the cart? Let us try to write. So, since we know that the horse is pulling the cart in the forward direction, we can understand that one of the forces acting on the cart is F1 in the forward direction. F1 is the force applied by horse on the cart in the forward direction. And the next force, so since F1 is acting in the forward direction, right? So the cart is moving forward because the net force acting, okay, along the direction in which force is applied by horse. Fine, no problem. And two more forces acting on the cart, that is the weight of the cart vertically downward and the normal reaction by the floor in the upward direction. Both the weight and normal reaction equal and oppositely directed. That's why there is no motion of the cart in the vertical direction. Either up and down the cart is not moving because normal reaction and W weight are becoming equal and oppositely directed. Fine. Since F1 is the force applied by horse on the cart in the forward direction, cart is also moving in the forward direction. Okay. Then what is the acceleration of the cart? According to Newton's second law. We can write that F1 equal to mass of the cart, let it be mc, into acceleration A. Now acceleration of the cart equal to F1 divided by mc. F1 divided by mc. Is it correct? Is it correct equation for the acceleration of the cart? Just keep a question in your mind. Again, we'll come back to the situation. Next thing is, let us consider horse as a system. Now we are looking at horse. Remember, when we have decided a system, what are the forces acting on the system only should be considered, but forces applied by the system should not be considered. Now in the list of forces acting on the horse, we should not consider F1 into consideration. So the forces acting on the cart, right? The forces acting on the cart are, sorry, forces acting on the horse. Forces acting on the horse, we are going to list out. So observe the diagram properly. So forces acting on horse, this we need, force acting on horse. So just before we are told at starting, cart is applying a force F2 backward. Cart is applying a force F2 backward, right? That is correct. So force is acting on horse, right? On horse. First one is F2, F2 by caught in the backward direction. And one more thing, there will be weight of the horse, weight of the horse acting vertically downward, weight of the horse, and normal reaction acting vertically upward. This is okay. Weight of the horse acting vertically downward, normal reaction acting vertically upward. Both are oppositely directed and equal in magnitude. So these two will be cancelled out. Net force along the vertical direction becomes 0. Along the vertical direction becomes 0. That's why there won't be any motion of the horse either up or down. Now, so weight of the horse vertically downward and normal force vertically upward. Okay. Now along the vertical direction, net force is 0. Net force is 0. That's why no motion along the vertical direction. No motion along the vertical direction. See here, the cart is applying a force F2 in the backward direction. But in practical situation, we can observe that the horse will move forward. We can observe that. See, even though the F2 is the force applied by cart on the horse in the backward direction, but horse will move forward along with cart. Let us suppose if the horse is moving backward, since the force applied by cart is acting backward, what will happen? What will be the scenario? So as the force is applied by cart in the backward direction, then the horse should move. Let us suppose the horse is moving backward and cart is moving forward, because F1 is the force acting in the forward direction on the cart. So cart is moving forward and horse is moving backward. Then what will happen? Then the horse will kick off the passengers, driver, everybody, and sit on the cart. So is this happening practically? Is it happening practically? Tell me. No, it's not happening practically. Then where did we commit the mistake in this scenario? In this situation, what is the mistake we have done? Here I am going to draw one more fresh diagram with modified FBT. So what is that? Let us see that. See here, when cart is being pulled by horse, when cart is being pulled by horse, okay, this is the forward force applied by F1, right? And this is the backward force applied by cart on the horse, F2, right? This is correct. But when the horse is pulling the cart, first it has to take the support of ground. It has to push the ground. This horse should push the ground. Okay, ground. Then in what direction the horse is pushing the ground? Along the same line, in the opposite direction, normal force will be acting. Means the horse will push the ground in this way. Then the normal force will act like this on the feet of horse. See, this is the normal force. It will have two components. One is horizontal component, that is n cos theta, and this will be the vertical component of normal force, that is n sin theta. This vertical component of normal force is balanced or cancelled out by weight of the horse. So along the vertical direction, net force has become 0. Here the horse is applying, right? The horse is applying a forward force F1. It is the forward component, and this is again forward component. Along the vertical direction, net force is 0. See here, this is the force acting in the direction of the force F1. The direction of F1 means this is a non-inertial frame and this is inertial frame. Initially it is at rest. First horse will try to move. First horse will move. Then the cart will move. Okay, right? So what will be the acceleration of the cart now? What will be the acceleration of cart? F1 is the force acting on cart, right? And similarly, n sin theta is the force acting on the horse, and that force will be added up to this. Okay, so this is a pseudo force here. This is a pseudo force, right? The cart will be at rest. The cart will be at rest until this F1, the combination of both F1 and n cos theta dominates the force F2. Dominates the force F2. Then we can write the acceleration of the cart as A equal to, let it be n cos theta as just F. So A equal to F1 minus F divided by mass of the cart. This will be the acceleration of the cart, right? Understand? Now so F minus F divided by MC. Similarly, when cart is applying backward force on the horse, this is the acceleration of the horse. See, cart is applying backward force. F2 on the horse. But there is a force, right, acting on the horse in the forward direction, that is n cos theta. Then this will act, the force, okay, F1 will be, F2 will be acting until this F1 combination and n cos theta will dominate this F2. So F1 minus F minus F by H, mass of the horse. So this will be the acceleration of the horse. Now next, when we are considering the cart, see, F1 is the force, right? F1 is the force acting on the cart. At the same time, when this cart is pushing the ground, down, then the ground also applies a normal force, okay, in this way, right? This also have a backward component and a vertical component. So this is, let it be F dash. The force F1 will act until it dominates this F dash. So acceleration of the cart is, that is F, because F1 equal to F2 here. So you can write it as F2 minus F dash. Here this is just F. It is just F. Okay, F dash divided by mass of cart. See, both will have same acceleration. Since here cart and horse both will move together, so both the cart and horse will have same acceleration. Both cart and horse will have same acceleration. Same acceleration. Okay, so these are the accelerations of the cart, right? And acceleration of horse. So acceleration of the cart equal to f1 minus f divided by mass of the cart, and the acceleration of the horse it has f2 minus, right, this is f dash, f2 minus f divided by mass of the horse. Both will be equal. When you are observing the motion of the horse and cart, both will move with same speed. Horse and cart, both the horse and cart will move with same speed. Its acceleration and cart's acceleration will be same. So these are the horse and cart concept, right? So I hope you all understood. If you are not understood, once you go through the textbook, and still if you are having doubts, you ask me. Thank you. See you all tomorrow.